Thank you.
Okay, sure. Okay, so last time we talked about O notation, and remember what that was. We said that if we have a function and it's going to be a function, we're going to always consider our functions having a domain of positive integers because we're in discrete mathematics. And so we really care about that. And when we get to the next section here in a little bit, you'll see why this is so important, why we really only care that we have a function that has integers for the domain. So going from integers to the real numbers, then f is O of g if there are positive real numbers c and n naught. When I say n naught, I mean n sub 0. If I can find c and n naught such that the constant time c times g will always be above, greater than the function, at least once that we get past a certain point for n, and that's where the n naught comes in, okay? So think about it this way, that if we say f equals O of g, look at that O, g, and think of that, you see the O there, and you see, okay, that means that g, or a constant multiple of g, will be an upper bound for f, okay? It will be an upper bound, g will be an upper bound, at least after we get past a certain point for n, right? So we did all that, and so we kind of just, this is just a repeat from last time. So, and it turned out, I don't think I had a slide that looked like this, but we mentioned this, but I wanted to kind of maybe put it a little bit more succinctly. It turns out that if we have a polynomial function, and by the way, if you don't remember what polynomial means, it's when we have a function with a bunch of terms that have different exponents, different integer exponents on our variable. So if I have a function called f of n, and then I have these different terms, n to some power, n to another power, and so on, and then if I order them so that the highest power goes first and then go all the way down, then it would be in this form here, and that would be, considered a polynomial. And so what we learned is that we could take any polynomial and show that it's O of n to the k, where k is the highest power here, right? Let me just kind of pull some examples out here. So here's a function, and this function here is, we learned last time, we could say that that is O of n to the fifth. Remember, we had a trick, and I'll kind of show that trick here in a minute to remind you. But it turns out that all we need to do when we have a function, a polynomial, is we say it's O of whatever the highest power here is. So we ignore all these others and ignore what's in front and say, yeah, it's O of n to the fifth. And what does that mean again? That we can find a constant multiple of n to the fifth that would always be above f of n, at least at some point past a certain n, right? Okay, and here we would say this is O of n to the third. So, this is where it comes down to that very simple rule. It's not hard, right? But we want to understand what O means, but it really comes down to, we can just get the highest degree term and get rid of the constant in front, and then say it's that, O of that, okay? So this would be O of n squared. And this, there's just a 1n there, so that would be O of n. So, simple enough. And remember the way we proved that, for each individual one. We didn't talk about it in general, but for each individual one, we did some examples where we said it comes down to these rules here. But we did this, we went through this process, so I'm going to just kind of remind you what this is. If I have this as a function here, what I can do is write almost the same thing down, but drop any terms that have negative coefficients. So over here, I'm going to drop the -3 to the third. All the others are positive. I'll drop that, and then I'll look and I'll say, compare these. Well, if I drop something that's negative, that can only make this bigger, right? So this here is bigger. So that's why I have a less than or equal to, because I dropped the negative term. But then we did another thing here. Remember, we pumped up the exponent off on the n here. So this was an n to the third, and I'm going to make it n to the fifth. And this was just a plain 2, and I'm going to put an n to the fifth there. Now, I can't just do that and say it's equal because it's not equal. But if I pump those up, then again, these are only going to get bigger than what they started out with. So that's why we could say that the original function is going to be less than or equal to what we get when we do those two things. Drop the negative term and then pump up these. And then if we pump these up so that they all have the same exponent, we can combine like terms. 3 plus 7 plus 2 is 12, and we get 12 n to the fifth. And we've shown now, because that this f of n would be O of n to the fifth, because remember, what does it mean to be O of n to the fifth? It means that we can show that some constant multiple of n to the fifth, in this case, we found it to be 12, would always be above our original function, at least above a certain n. But now what this said here is it's always going to work for a polynomial for even starting as low as n equals 1. So n naught is going to be 1. It's going to be true for anything bigger than or equal to 1. And then did our constant that we found end up being, follow this rule? It says the sum of positive coefficients. Well, we look here and say 3, 7, and 2. Yep, 12. So, if we knew this rule, you could go straight to down here and you could say, okay, yeah, it's O of n to the fifth, and C is 12, and n naught is 1, based on these rules. But I do want you to be able to go through this process and show me, for the test, I want you to show me how you know that. Okay. So that was the general process for a polynomial, to show that it's O of n to the whatever the highest degree is. Okay, so now let's go on to omega notation. So it's just the same thing, but we're looking at a lower bound. So here we're saying let f and g be two functions, and if we can find real numbers c and n naught, such that as soon as we get past a certain point, past n naught, then the constant multiple times g is less than f of n. So, f of n is greater than it, so this would be less than, and then or equal to, right? So anyway, but this is going to be lower or equal to f of n. So it's the same thing, but we're saying before it was, we had a less than or equal to sign here, and now we're having this. And so that if we can say that, then we would say f is omega of g. And this is the omega symbol here. So here, what you want to do, before, I said, look, if it says O of g, then think of g, a constant of g times g being an upper bound. Now, when it's omega, you say f is omega of g. What does that mean? It means if I can, g, here's this function g, I can take a constant multiple of it and a certain constant, so that, and show that eventually, given once we get past a certain value of n, g is going to be below f. C times g, the constant multiple of g, will always be below or equal to a lower bound of f. Okay, so it's just the opposite. So you have to turn your mind around and start looking at that as that way. So in other words, if we say f is omega of g, then we're just saying that we know there's a constant c, such that when we multiply g by that c, it'll eventually stay below f. G will be a lower bound. Cg will be a lower bound. Okay. So, we can look at these examples here. Here's an example of, we've got the red function and the blue function. We've got, first of all, this first one, x to the third, y, and then x squared. And I might want to ask, is if f is the red one and g is the blue one, is F omega of G. So that I'd look at that and say, does that means, can I find a constant so that that constant times G is always less than F? Well, yeah, because look at this first one here. I don't even have to look at the second graph, but this first one here, it's already true for C equals 1, because 1 times G is the X squared, and that's this this blue line. And once we get past this certain point right here, yes, G is always going to be below the red. So we would say yes. And here's my C. C is 1. And that's true for anything past this right here, which would be 1. And you could say, well, and we only have to find one C that it's for which it's true. But you see that no matter what you have here, if I were to have a different F, where I have a constant in front here, then you might think, well, no, it's not. This now F is no longer omega of G, but it really is, because right here you think, no, G is not a lower bound. The blue is not below it, but eventually it will get there. So it turns out that even anything that we have as far as a constant in front of this X to the third, we're still going to find that X squared will eventually be the lower bound, or constant times X squared will eventually become a lower bound. Okay, so now, we just said that a polynomial of degree K is always going to be O of n to the K. Well, this is telling us that a polynomial of degree K will also be omega of n to the K. Remember when we were talking about upper bounds, we said now upper boundary doesn't help us that much. I could say I don't make any more than $3 million a year. Well, that doesn't tell you much. It's an upper boundary, but I don't make anywhere near $3 million a year. So it's an upper boundary, but not a very, doesn't tell you anything. And even a lower boundary, I could say, well, I make over $10,000 a year. And, again, that's not telling you much, because it's such a low, it's such a, those aren't very tight boundaries, right? So ultimately our goal is to find some tighter boundary. But what we're going to do first, we talked about the upper boundary. Now we're going to talk about a lower bound, and then eventually put things together to somehow show what might be considered maybe a tight bound, a tight, yeah, bound. Oh, that doesn't sound right. Upper bound, lower bound, and a tight bound. I guess that's right. Tight bound just didn't sound right to me, but okay. Anyway, so we've already done this we found that F is O of n to the K, but it turns out that if F is a polynomial, it's also omega of n to the K. Now, okay, so let's look. So if this is true, then I would take this function and say that's omega n to the 5th, because the highest exponent is a 5 here. If this is true, then this function would be omega n to the 3rd, and so on. This is n to the 2nd, and this is just a plain n, so it's omega n. Again, that's the lower boundary. Now we can get a constant times n to the K that would be the lower boundary. Now, one thing to note is this is not true when when the leading coefficient, the coefficient in front of the term with the highest degree, is negative. If I have a -3 here, then that's going to be this blue curve way down here. And we see that G will never be a lower bound for that. Any constant multiple of G won't be a lower bound for that. Okay, so it's not true when that leading coefficient is negative. But we're just saying if it's positive, then this is true, and it's pretty easy then to remember. And here's how we're going to show it. Again, you could just remember the rule, but I want you to be able to show it. So here we've got F of n, and then n squared, and we want to say is f omega of g. Yeah, because you know the highest degree of f is n squared, and so g, if g is n squared, we just found that f would be omega of g. But how do we show that? So, you know, in order to show it for this example, we need to find a c and an n naught, such that the c will be the multiple of g that we use, and then the n naught will be the value at which anytime we go past the value n, we would have g times you know, c times g being the lower bound. Okay, so again, this is what we do. This is the rule. So, but here's how we would do it. Okay, so we know that this is the rule. Oh, did I go over the rule? Oh no, this is the first time I'm showing you this rule. Sorry. I was thinking, yeah, did I tell you this yet? Okay, I didn't say this yet. Okay, so here's what we do. We know there's this, we would use this for C and this for N naught. Okay, so C would just be our A sub K, which is the leading coefficient, the coefficient in front of that first term. Okay, and then N naught is always going to be 1, just like it was with our O notation for polynomials too. Okay, so so it's saying that's the rule. You could just use it, but let's show it. So here we go. We have this 3n squared plus 2n plus 1. If f has no negative coefficients, then, and this doesn't have any negative coefficients, then here's how we show it. We just drop the terms that don't have the highest degree, because, and then compare. If I have 3n squared compared to this other one, well, the 3n squared is only going to be smaller, right? Because I just dropped some positive terms. I dropped some positive terms, so so this is going to get smaller, which means the original was bigger. So, and that's how we now we've done it. We've shown that f of n is greater than or equal to a constant times n squared for any value past a certain point. So we've shown that omega is that f is omega of n squared. So so then we've shown it here, so we would say that. So really all you do when when there's no negative coefficients and we're trying to show omega of something, then we just drop everything except for the highest degree term, and then we know that c is going to be that thing that's right in front of that highest degree term. So it's true for c equals 3 and n greater than or equal to 1. Now, what if it has negative coefficients like this? We can't do that same trick of just dropping those extra terms, because it's not going to be less than 3n squared, because we're dropping some negative values. So you know, it would be greater than. So here's the rule for this, and this was a little bit involves a little bit more, but once you get through it, you realize it's not that big of a deal. The rule is this: if you have negative coefficients here, and you're trying to show what the omega is, then this rule says that for C, you can use the leading coefficient divided by 2. Okay, so this is the 3 leading coefficient divided by 2. That would be my C. Okay, so 3 divided by 2, that would be what I'd use for C. Then it says, okay, what do I use for N naught? Well, first of all, we've got this. Well, first of all, let's look at A. It says, let A be the sum of the absolute values of the negative coefficients. So let's look in this case here. A is the sum of the absolute values of the negative coefficients. So I'd have absolute value of -4 plus absolute value of -2. So I'd have a +4 plus a +2 gives me a +6. So A is equal to 6. Then we're going to look at 2a divided by a sub k. Okay, what's that? Well, A is 6. So we're going to have 2 times 6 divided by A sub k. And again, what's A sub k? Remember that just denotes the, the constant in front of the, term that has the highest degree. And so that this would be the n squared. And so it would be the 3. So 2 times 6 divided by 3, that would be 4. Now what we do is we look to see the maximum of whatever we get here along with 1, because basically sometimes, depending on what the numbers are, you could get something less than 1 here. If you got something less than 1, you're not going to say n naught has to be greater than 1/2, because we're talking about positive integers. So the first starting point is n equals 1. So they're saying, just, whatever number you get here for the 2a over a sub k, whatever that number is, check it against, 1. And if it's bigger than 1, then that's your number. But if it's smaller than 1, then you're not going to go with that number, but you're just going to go with 1. So find the maximum of these. And in this case, it's 4. So I would, yeah, go ahead.
Do we need to know how to prove these rules?
Well, that's a good question. Now, see, the last one, I was just going to say that this last one, I want you to be able to do this one, right? Okay.
Yep.
Now, when it comes to this, I had a nice little proof out here to show this for this particular example. But here's the deal. It was a little bit more involved, not terrible, but we have so much to cover. I decided I don't even want to take the time to go over this proof because it just makes, we just don't have time since I need to cover everything else. So what I was just about ready to say is, don't worry on this one. Don't worry about showing me on this one. You can just take and if you want to see that proof I had, let me know. I can send it to you by email. There's a way to show for any example that this works. But anyway, for this one, I'm not going to have you do that. And you don't have to do that in Zybooks won't make you do that for any of them for that. Okay, so, but just go ahead for this one, just know the rule and be able to come up with a C and an N naught. Okay. Okay, so here's the summary for the omega. When we have a polynomial, we know that f then is omega of n to the k. And here with, here's the no negative coefficients. We just pick up the leading coefficient and use n naught of 1. If it has negative coefficients, then, we do all this stuff here. Okay. Okay, so now, again, we've talked about upper bounds and we've talked about lower bounds. But again, those aren't really helpful in and of themselves. But if we can find a function g such that in one case, using one constant, we could say that, f is O of g because of one certain constant, but f is also omega of g. That means, the opposite, but it would be for a different constant. If we can say both of those are true, then that gives us a great idea on what the shape of the function is, right? So if I say I got a function here and this other function is always going to be a lower bound. No, sorry, not always, but it can be a lower bound given a certain c. And this same function can also be an upper bound given another c. Then what that means is I'm pushing my lower bound and upper bound and saying they're the same, just I have to use a different c. But in reality, what that ends up doing is just saying that f and g are basically shaped the same way. Does that make sense? They're shaped the same way. If I can find a c such that cg is an upper bound, but I can find another constant k where kg is a lower bound, then basically, we're saying that as things get big in the, in the positive direction, which is what we're caring about, then they're that's saying something. That, we've squeezed the upper bound and lower bound, and we've got some same function. It's f is O of that, and it's also omega of that. So if that's true, if we can say that, then we can say that f is theta of g. Okay. And again, ultimately, it kind of comes down to it's going to be kind of shaped like that. And it would mean it has the same rate of growth. G would have the same rate of growth as F. And another way to say it is F is said to be of order G. Okay. So again, if we can say F is O of G, but F is also omega of G, then we say F is theta of G. So now let's look at kind of putting all this together back at our polynomial. In the book, they're showing this polynomial again, and for some reason they wanted to call it P now because it's a polynomial, but you know, we've been calling our function that we're looking at F all along, so you can call this whatever you want. But we'll have this function here. It's a degree K polynomial. It's saying as long as the leading coefficient is positive, which is one of the things we said a minute ago for omega, for that omega situation to be true, right? As long as this is positive, then that function is theta of n to the k. And how do we know that? Well, we just said a polynomial of degree k is O of n to the k. We said that earlier. And then we just said that a polynomial of degree k is omega of n to the k. So that shows then that based on what the definition of theta is, then that function is theta of n to the k. So here's where it comes down to, it all comes down to just a very simple rule that that a third grader could have learned, but not known what it all means, right? Okay, so it's a simple rule, but you know, you wouldn't know what it means unless we'd gone over it here in class. And I want you to know what it means. But anyway, so here we go. Here's a function. We know that it's, if the highest degree is 2, we know that f is O of n squared, but we also know that f is omega of n squared. So by definition, f is also theta of n squared. So all we do is just drop the terms except for the term with the highest degree, drop the constant, and then it's O of that, it's omega of that, so it's theta of that. And what does that mean? That means that this function here is going to be, you know, similarly shaped as n squared. Now it's going to be longer or wider or something like that, but it's you know, of that same family. Okay, so that's a lot to say of what we could probably have said. We could have probably maybe guessed that, but this is,
So
yeah, go ahead.
I think I'm confused on the omega one on this
Okay.
one. You would have to use the sum of the 2 times the negatives and all that stuff, right?
Yeah, you'd have to do
And that
that.
still ends up at n squared?
What's that?
And that still ends up at n squared?
Yeah, it does. And in fact, let me just go back here. We actually,
Is that the same example?
yeah, well, we actually said this, that we can always say if we have I went back, a polynomial of degree k is always going to be omega of n to the k, as long as that first term has a
Okay.
positive.
Yep. I apologize. I
Okay.
missed that one. Yep.
No, that's okay. No, that's okay. So, and yeah, you know, at this point you might say, well, let's show this, but at this point we're going to now kind of say, well, we've learned it, so we won't have to now, you know, we're not going to be having to prove these things anymore because now we've learned that, yeah, that rule. Okay. So here, f, the highest degree is 3. So f is O of n to the third. It's omega of n to the third. So we could say it's theta of n to the third, or we could say f is of order n to the third. Here we have this function. It's a linear function. What would we say f is theta of here? Anybody want to say?
N?
Of n, just plain n. right. So because, again, we're looking, this is a polynomial, although a very simple polynomial, and the highest degree is 1. So we would say it's O of n to the first, and it's omega of n to the first, so it's theta of n to the first, right? And here, what would we say? If this is f, what would we say f is theta of here?
N cubed.
Yeah, n cubed, right? So we just take that. Okay, so now this theta now finally means something. Again, the upper bound didn't mean anything because I could have said I make less than $3 million. The lower bound doesn't mean anything because I could say I make at least $10,000. But the theta is narrowing down, as saying we got something, this could be above and it could be below at the same time. So we've narrowed it down and said, this is the shape. Okay, questions at this point? Okay, if
I'm
not.
sorry, I apologize. I'm
No, go
assuming
ahead.
this is all just for, yeah, I guess that's what the theorem says, but we only use this in polynomials, right?
Right, yes, so far. But we're going to find then some other rules too. But yeah, for polynomials, we know it's as easy as this. Yeah.
Okay.
No, so here's a new one. This isn't a function that involves logarithms, isn't a polynomial. So, but this is also a rule we're learning, that anything, any function that has a log in it, like this, just a plain log, base anything, whatever the base is, greater than 1. Log base a of n is going to be theta of log base anything else of n. Now, don't let that confuse you. Basically, what it's saying is, I could say log base 2 of n is the same thing as it is theta log base 8 of n, or theta log base 10 of n. I could put anything in here, and we don't care about that. We just want to come up with one theta. So here's the deal. Usually if we leave off, the base right here in this log, that just means it's a 10, right? If you leave off the base, it's a 10, means it's 10. So since this is true for any base, then for b then and 10 is greater than 1, then we'll just usually write it this way. So it's kind of just convenient. Since we know that it works for any base, we'll say, okay, to make it simple, anytime I have a function that's just a log function, I'm going to say it's theta of log n, not saying the base, but we know that means log base 10. Okay, so that's just, again, pretty easy, a pretty easy rule. And we're not gonna prove that or anything. Okay, so we're just gonna accept that. Okay, so here again, we could have, it's also theta of log n. Okay, let's go to the constant function. A constant function would just be f of n equals some constant, doesn't depend upon n at all. So we would say that is theta of 1. And that'd be a pretty simple proof to show that we could take 1 and find a constant such that the constant's always greater than this, and take 1, find a constant such, and find that the constant times this is less than this. And so therefore we've got theta of 1. But eventually you just get to know, yeah, a constant function is theta of 1. Now, last time when we looked at all those graphs, we saw that some went up faster than others. When when moving to the right, they had greater, rates of change as we got bigger and bigger. And I had ordered them so that the ones at the top were more flat, and then the ones further on down got higher, would go up quicker and quicker and quicker. Well, that's what they do in this table here. They've kind of named these functions and are saying this: if I have a function that's theta of 1, well, that means it's constant. And you know what that looks like? It's just a straight line straight across. But then as we get further on down here, all of these, anything that's theta of these further down are going to grow faster than the constant. So theta log n, which is weird, and I don't know why they even include this in the list, but that's okay. That ends up growing a little bit faster than the constant. Log of n ends up growing a little bit faster than this one above. N by itself is a line, and so that grows faster than a log. So anyway, any functions that are theta of this or theta of that and so on, we can kind of get the idea. Well, something that's theta of n is going to grow faster than something that's theta of 1. And just so that we see that this order, and we kind of saw that with when we looked at the graphs the other day, it's true that this is in the right order, so that as we get everything below, so each function is O of the functions below it in the table. Okay, so I could say a function an n squared would be O of n to the third, because n to the third would always be above n. But basically, I don't know, they say this, I don't want that to confuse you, but as we, basically what I'm trying to say is as we go further down in the table, we're going up faster and faster, our lines, our curves. And then it's the same thing with omega. If you go, if you look at something below, you know that something above is going to be, well, any function is going to be omega of any of the functions above it in the table. But again, if that confuses you, just realize, no, anything down here is going to grow faster than anything up here, right? Okay.
Why do they call it algorithmic complexity?
Oh, that's funny. I don't know why they called it that, because that's what we're going to talk about next time. I mean, today in 2.2. And I just pulled this out of the book. So it's funny. And that's from 2.1. So I guess they were getting ahead of themselves. Yes. Okay. So let's, pretend like that's not there because what we're going to do in 2.2 is we're going to say, hey, we can apply all of this to the, to figuring out the complexity of an algorithm. So so we'll eventually get there. So just pretend like this is just saying we've just ordered these and this is the order. So good question.
So what you're saying right here in the n squared is O of n cubed and n cubed is omega of n squared in essence. That's only true when there's not any coefficients. Otherwise, you'd have to say n squared is O of n cubed when c is x or greater than x, right?
Well, they're kind of mixing things here. I mean, because they're saying these are thetas here. They're saying theta, but I think what they're trying to say is that if I had a function that's theta n, so that could be a 5n plus 2, right? 5n plus 2 could be this. And that's going to be omega of that's going to be
omega of n squared.
Yeah.
But at any point, so if you were at x equals 2, it's still going to be omega at that point, or do you have to decide?
Well, we say that at some point, and that's all that when we talk about O and omega and
so
theta,
we're only describing
we're just saying at eventually.
Okay.
And we're not going to worry about when. So okay. Now, the book doesn't show where, as we get, it has an n squared and an n to the third. It doesn't talk about, what happens as this exponent gets bigger here on n. What happens? Because we see that we do have the constant function, then we have this log function. Here's the linear function. Here's the n log function. So we're starting to go up quicker and quicker. And then n squared and then n cubed goes up even quicker, but then the exponential goes up quicker than that, and n factorial goes up even quicker than that. But where does it fit in where we have something like n to the 1,000th? They don't say, and you might guess that maybe it would go in here, but you might wonder, is there a number such that n to that number, like n to the millionth, would that maybe end up going up faster eventually than 2 to the n? The book didn't say, okay? But one of the questions that's asked in the book depends upon you knowing this. So I'm going to tell you right now, here's where something like n to the 1,000 fits in. So all of the n's to the powers, as the powers go up, they're all here, but never do they grow any faster than the exponential. Exponential always grows faster than n to any power, okay? So just know that fits in there, right there, okay? Okay, so now we also have some rules that we can use because sometimes we've got functions that we're comfortable with, but then we have a function that's got some terms, like maybe there's a function with a logarithmic term and an exponential term. What happens then, when we've got, two different terms, one grows really fast, one goes really slow. How are we going to evaluate the overall function? So that's where some of these rules come into play. Now I'm going to just put this here. We'll look at some examples here in a minute, but I wanted to say, first of all, let's go past the first two. Let's just start with the number 3. And then, like I say, I'm going to give examples here in a minute. But this third one's fairly simple. It says, if f is O of g, then c times f is O of g. And that makes sense, right? I mean, just taking any function times a constant, it's not going to change the shape of it, right? And not change the asymptotic growth. Same thing for O, and then also for omega. And we could prove that pretty easily because, in the proof, we're talking about putting a constant in front. So anyway, so that's kind of hopefully kind of obvious. These last two are kind of like what I would consider, I don't know if they would be actually termed this, I would consider the transitive, kind of like a transitive property, because this says if f is O of g, but g is O of h, then f is O of h. Okay, so, we've got this chain here. And this says if f is omega of g, but g is omega of h, then f is omega of h. So that's kind of this transitive thing. Now these first two, this one says that if there's a function that is an upper bound to f, and that's also an upper bound to g, then it's also going to be an upper bound to f plus g. Okay, and this second one says if we've got something that's a lower bound to f, or it's a lower bound to g, doesn't have to be lower bound to both, but if it's a lower bound to either one of them, then that's going to be a lower bound when we add them together. Yeah, so here's where we can use this kind of thing. Let's say we have a function that looks like this. Okay, we've got kind of a polynomial term, and then a term like this, and then an exponential. What are we going to say it is? What if I wanted to say it's theta of what? Well, gosh, there's all these different O's and omegas and everything. So what could we say to that? Well, first of all, the first thing they do is say that, we know that this first term, we'll look at this first term first. It's O of n to the third, right? We know that. But n to the third is O of 2 to the n, right? 2 to the n grows faster than n to the third. So this is one of those transitive things like down here. Therefore, 5n to the third is O of 2 to the n. Well, it's also O of n to the third, right? But what we're doing is pumping it up to get equal to the highest, the quickest growing one. We're basically looking at this quickest growing one and trying to show that all of these are O of that, okay? So we get O of 2 to the n. Then this other one here, the log function here, log part, it's O of n log n, just drop the constant. But n log n is O of 2 to the n. If you think back to the chart, 2 to the n is at the very bottom of the chart. It's always an upper bound for anything else above the chart. So that's true. And so again, this transitive thing says then that this is O of n of 2 to the n. So what we do is then, so we've got, and then of course the first, here it's saying the third term, 5 2 to the n is also O 2 to the n, right? So we were able to show that all of these, even these slower growing functions, are at least are O to the n, 2 to the n. It can be an upper bound. So if that's the case, then that's true. That's an upper bound for each individual function. So when we add them together, it's also an upper bound. So that's what this first rule says here. Okay. Then now we're doing it for the omega. So we say, we know it's omega because omega is 2 to the n. Okay, sorry. First of all, 5 times 2 to the n is omega 2 to the n. We know that, right? Because it's just a constant times that. But then now we're using this second one. If we've got a lower bound on one of these terms, then it's going to be a lower bound to all of them. So therefore, we can say all of these added together will also be omega 2 to the n. Well, so now what have we shown? We show that f is O of 2 to the n. F is also omega 2 to the n. So therefore, f is theta 2 to the n. So what this comes down to is this. What this has shown here, using these rules, in this example anyway, and we could show it's always true, is that the highest, the quickest growing term is the one that ultimately defines the asymptotic behavior, right? So the highest growing term is 2 to the n, and so that's the order that this function is, and we showed it here. Okay, makes sense?
So what is the use of this though?
Okay, well, we'll see the use in the next section. You mean as far as knowing why we even care about all this stuff?
Yeah, what's the benefit of finding theta 2 to the n?
Okay, yeah. Well, for right now, we can say that this function is, its behavior as n gets big is similar to 2 to the n. Okay. It's similar there because if it's O of and omega of, then it's going to be similar to. But yeah, we'll see that in just a minute. I'm going to be done with this, and then I'm going to go on to the next section. So I tell you what, since I want to have plenty of time to go on to the next section, I'm going to go past this and not spend time on it. I hope you can go back to the notes and check this out. I have arrows showing why we know all of this. I got these questions, and then I'm pointing to the rules that would say, let us know this. If you look at this and don't understand any of it, email me and I can, we can talk individually, or I can send you an email and explain it to you. Okay. So, but those are just some examples, and that by looking at these rules, hopefully you could figure that out. But
are you recording everything if we can go back? And
you know what, that's a good question. Normally I was not, but someone was going to have to miss today, and I had said that I would record. So I am recording this lecture. And since this is such a weird, difficult one to follow, and I'm having to go so quickly, I tell you, I'll go ahead and let everybody have access to this one. So I will let you go back and watch this again.
Okay, so, thank you.
Okay, sure thing. Okay. So then I was going to have us do this challenge activity together where you rate the functions, but again, we didn't really have time. So hopefully after you look at this, and then you can go to that. But basically think about it this way, guys. The growth rate is always going to be determined by the quickest growing term, okay? So if we've got an n factorial term in there, that's going to be the fastest growing one, even though we also have a +3, right? If we have 2 to the n, and we have a bunch of other stuff, the fastest, but no, if, whatever the highest, the one that's lowest down in the chart, that's the fastest growing one. That's the one that's going to have the highest growth rate. I mean, that's the one that's going to have the same growth rate. Okay. Okay, so that takes care of that one. And now we will talk here these last 15 minutes or so on why we even care. Okay, so all of that just to be able to say why we even care, because this whole section is on computation, and we're gonna talk about algorithms. We already kind of talked about algorithms very first section. We're going to look at algorithms, and what our ultimate desire is to be able to look at an algorithm and to say, how complex is this algorithm? What's the complexity? Is this going to take a lot of time and a lot of memory to do? Okay, so kind of keep that in mind. That's kind of where we're going with it. Okay, so computational complexity is the amount of resources used by an algorithm. Now, an algorithm would use time, and it also can use space, memory, right? So usually the way we would measure the efficiency of an algorithm would be in terms of the input size. What I mean by that is, let's say we have an algorithm that's adding up a list of numbers, okay? Well, no, let's say sorting through a list of numbers. And let's say I have this algorithm, and I've only given it a list of 3 numbers. Well, that's going to take a certain number of steps to sort. But if I give it 100 numbers, it's going to take many more steps to sort a list of 100 than it is a list of 3. So I would say that the length of my list is my input. How many numbers there are, that's my input, and it's more complex based upon how many there are. So usually that's how we can we end up, if measuring complexity is having to do with the input. But you'll see some examples here in a minute. Now, we're not going to talk about space complexity. We're just going to concentrate on time complexity, okay, in this class. Okay, so time complexity as a function. So here's what they say. The time complexity of an algorithm is defined by a function where our domain is positive integers and our range is positive integers, such that f of n is the maximum number of atomic operations performed by the algorithm on any input of size n. So we're going to say, here's an algorithm. What's the maximum number of atomic operations that would be needed to be performed? Okay, and sometimes, often, it would depend on the input as far as how many numbers we're inputting or something like that. And so that's why it would use it in our cases. Our examples we're going to see that many of them have relate to a certain number of inputs. So we'll call it a function of n, f of n. So time complexity of an algorithm is a function that really it just measures the maximum number of atomic operations for that algorithm. Okay, so let's look at this. I just took this off of the participation activity. You're going to be doing this participation activity, and I don't have time for us to flip through it, but I just wanted to kind of give you an idea of what this is all about. So let's look at this algorithm called compute sum. The input's going to be a certain few numbers and a certain length of numbers. So there's going to be n numbers. So it might be 3, you might put in 100. The output's going to be the sum of the numbers in the sequence. Okay. Now let's figure out how many atomic operations, atomic meaning, we'll try to split them down to say, well, this would be just worth 1, this would be worth 2, because it's doing 2 things in this case, or it's just doing 1 in the other case. So that's kind of what atomic means. So first of all, let's start at the very top. Sum equals 0. That's an assignment statement. So we would say that that's 1 atomic operation. Okay. Now we have a loop from 1 to n. Since it's a loop from 1 to n, that means this loop is going to be run n times. The iteration is going to be n iterations, right? Okay, and then inside here, we're going to be adding some things together, and then assigning that to sum again. So they've listed out here how many this is. So since the loop is iterated n times, and then the beginning of the loop here, we're going to count that as 2 operations because it has to test I to see where it is. And then it's going to increment I if it's ready to go on to the next one. You know, each time it goes through, it increments by 1. So we're going to count that as 2 atomic operations for just this line here. But then inside, we're going to count that as 2 because we've got 1 addition and 1 assignment. Okay, so altogether there's 4 inside the loop, but this is done n times. Then when it's all done, we have 1, we return. So that's one step. Okay, so let's find out how many altogether that is. Well, so you know, they counted up here. So this is 1 plus, and then n times 4, right? Because this 4 things are being done n times. So n times 4 plus this extra 1. And then we can, you know, add that together, maybe clean it up a bit, and we get 4n plus 2. So we would say that the time complexity function for this algorithm is 4n plus 2. Does that kind of make sense? Okay, if that's the time complexity, what's the asymptotic behavior? Well, that's just a simple little polynomial. We know it's theta of n. So that would give us an idea, you know, how it grows, theta of n. That's not going to, you know, as n gets bigger, it just gets a little bit bigger linearly, right? Okay. And so that's what we want in this section. We want to find the time complexity and then find its order, and it's order n here. So we'd say the time complexity f is theta n, theta of n. Now they show this little chart here, and they say, what if we're assuming, if we assume one little instruction takes 1 microsecond to execute, and you know, it's different on any computer, but they're just trying to come up with a standard, just saying, if it was always took this amount, and we had a time complexity function that was of order n, then that would mean that if our input is 10, then it's going to be 10 microseconds. Or if it's 100, it's 100 microseconds. So when we get up to 100,000, it's just a 0.1 second. But what if we have an algorithm that ends up being n to the 3rd in complexity, the order of the time complexity? Then an input of 100,000 would take 31.7 years. So it's just showing you that, you know, the amount of time that it can take for an algorithm, for algorithms, vary dramatically based upon the order of these algorithms. So that's why it's important to kind of learn about this. Okay, let's look at this one. What's the asymptotic time complexity of this? We have input of a sequence of numbers. We're just going to take the average of the first and last elements of the sequence. And so here are the instructions. Well, here we just have what we could call it 2 operations, addition and an assignment. And here we have a division and an assignment. So there's 2 on this first, there's 2 on this one, 2 on this one, and then here's a return. So that's 1. So it would be 2 plus 2 plus 1, which is 5. That would be the time complexity. And that's a constant function, and that is theta of n. No, that's wrong. I hope I didn't. I might have to go back and change it. I thought I changed that. I thought I'd found that mistake before. It's not theta of n, right? It's theta of 1. Okay, so that means it doesn't matter. You can give me 1,000,000 A's. Well, you know, that's when the space issue comes up. But anyway, the idea is that it does not grow as n gets bigger. Okay, here's another one. Here's a loop. Okay, so we've got a sequence of numbers, and it's outputting the smallest number in the sequence, and you could look through to see if that's really doing that, but that is what it's doing. So this first one, one is one operation. And then for the loop, we have iterated n minus 1 times because it's going from 2 to n, not 1 to n, but 2 to n. So we subtract 1 from n minus 1 times. Now inside the loop, you know, for this here, it's going to test I and then increment I. Now here, this might be worth 1 or it might be worth 2 because it's an if statement. So if this is true, then it's going to make the assignment. Otherwise, it's not. So we're going to say it's, you know, sometimes it's 1, sometimes it's 2. So they say all together here, the 2 plus this and then possibly this means that it's either 3 or 4 when we add these up here. And they say depending on the input values. Now, what we care about is the maximum number. So we would immediately go to, well, let's think of the worst case scenario and go with the 4, right? Okay, but okay, and then here one operation for the return. Okay, so that would just so that would be it. Okay, now notice all of a sudden we were talking about 1s and 2s and 4s. Now all of a sudden we're talking about C's and D's. Okay, where does that come in? Now, here's the deal. As long as we're talking about a 1 and a 4 and an 8, you know, it doesn't matter what number. If it's a constant, it's a constant, and that's not going to affect the order. And the other thing you could say is, well, wait a second, just how do I know that a comparison would take the same amount of time as an assignment? Maybe they wouldn't take the same amount of time. So you'd say, well, maybe this one's worth twice the time as this, and so on. So what we end up doing is not necessarily literally counting. I mean, you can if you want, but we would say, well, this is it's some constant. Maybe it's 3, maybe it's 4, maybe, you know, this takes 3 times as long as that, so it would be a 5. But so what we do is stop putting specific numbers and just say, well, it's some constant, and I really don't even care what, right? So we say C, it's going to be C, a constant number times n minus 1. So a constant number C times n minus 1. And then the other ones, which are outside the loop, here 1 plus 1, but let's say, well, how do we know they don't take the same time? So let's just say a constant. We don't care. It's just 2. Maybe it would count as a 10 or whatever. Doesn't matter. It's just a constant, and we don't care. So it's n minus 1 times a constant for the loop, and then another constant for those other ones. And then all together, we can simplify that, and we get Cn plus another constant here. And what order is that? It's theta of n. So this would be theta of n. Sorry, I need to, okay, I want to say something and get to another point. So I'm going to just, you just, from here on out, when you get to looking at the notes, I want you to go start here and just read through it, and you can learn some things that I didn't have a chance to say here, because it's almost, I have just a few more minutes, and so I need to say a few things, and then hopefully you guys can go and look at this and then be able to finish it off. But I want to say something here. The book, when they did this while loop, and they started, you know, assigning, you know, and here, this is back when they weren't using constants yet, you know, of C, D, and they're just using, okay, this is one assignment operation. Here, a while loop, it's gonna, the while loop is gonna see if it's not equal to, and then check if it's less than. And so we'll count it as 3, and because it's got an and there too. And then here, now they only counted that as 1, but I would say based on what they said before, this one would count as 2 because we've got an addition as well as an assignment. But again, it doesn't matter if we're, you know, it's just going to end up being, we're going to say it's a constant, so the constants won't matter. But anyway, so they add this up, but then they say, you know, what happens is this one's going to try to look for a number, and as soon as it finds the number, it returns. So it's not always, you know, going to go through the same number of times depending upon what sequence is given. it's looking for a certain number in a sequence. If it's looking for a 5 in a sequence, if the first number in that sequence is a 5, it's done, right? It's not going to go through all of these. So here's the deal. They're using this as an example of that there's a worst case scenario where you would have to go through all of them, not just find it the first time you check, right? So the book starts talking about this worst case time complexity function. But here's the deal, and it kind of bugs me. I think the author's off his rocker. Now, either that or I'm totally going crazy. But when he's talking about the worst case complexity function, he says the worst case time complexity function is defined to be the maximum number of atomic operations of the algorithm that the algorithm requires, where the maximum is taken over all possible inputs of n. Well, that's already built into the definition of time complexity. See, time complexity, the maximum number of atomic operations. So what he does, so this first makes sense where he counts it up and say, okay, I got 1 here in the loop. At the most I have, if I have to go through this all the time, it would be, you know, n minus 1 times. And then, and I guess we need to say, I guess that's not bad to point that out, that we're going to count the most possible times. Okay. So we, at the most, we'll go through n minus 1 times these 3 inside the loop, and then the 2 at the end. And so they end up with 4, putting all that together gets 4n minus 1. So, I mean, that's fine and that's good. And that's, I see, yeah, you know, we'll always say, let's check the worst case scenario. But here's where I just don't get what the author's trying to do. From here on out, they start talking about, well, here's this function has it, you know, well, find a O of something and a omega of something so that I can say it's theta of something. Okay, so they're going to be always talking about lower bound, upper bound, and then try to come up with this. Really, here's the deal, guys. Once we find what we think this function looks like, that's the time complexity function. It's not that it's less than something or greater than something. That is it. That's it. So, and we know based on our on the rules that we just found in the last section, if the time complexity is 4n minus 1, then we're going to say that f is theta of n, right? F is theta of n. So I think he or they or she or whoever are complicating it way past what it needs to be, and it doesn't even make sense what they're doing, I don't think. Find this. So I'm saying don't worry about all of that they say there. So when the author finds a time complexity function and then starts talking about, but here's the upper bound and here's the lower bound, ignore that, just find the time complexity function and then determine what the order of it is at that point, okay? So I would say at this point here, f of n is 4n minus 1, so the order is theta of n. Okay, that's all I would say. Okay, and for this one here, well, you can go through and look at this, but this is another one where it's got a, I thought I had a, shoot, I was going to do a, I was going to do this beforehand. I'm sorry, I'm going to skip ahead real quick. Here's a loop inside of a loop, okay? A loop inside of a loop. The first one, we're making an assignment. We'd call that 1, but let me just call it B because again, we don't care the number really. And then the loop, we're going to go through n iterations of the loop because it goes 1 to n. But then inside the loop, we're going to do this. So again, let's just call it C operation. And then we have a loop inside. Here's an inner loop. Well, that is going to go through n iterations of that loop. And then inside there, we're going to do, let's say that represents a constant called D. Then number of operations is going to be the B plus the N times all of this, what's inside it. And what's inside of this outer loop is the inner loop, which is D times N plus the C. Anyway, so Oh, it's past time. Okay, I gotta go. I'm gonna let you guys look at this on your own and do these. I have a lot of examples here. So I hope that you can look at this and look at the examples and then try to do them. If you come up with questions with anything, send me an email. I'd be glad to work with you individually, or just send you, say, I don't understand why this is true. And I'll write back and say, it's because of blah, blah, blah. Okay, so feel free to do that. And I'm so sorry, again, I don't know how they're expecting us to get through all of this material in such a short time, but anyway, so what I'd like you to do for the assignments is to do all of the participation activities and the challenge activities from 2.1 and 2.2. And none of them are requiring you really to talk about the that upper bound, lower bound thing that I said to ignore. So, but you can still answer the questions about them. So let me know if you do have questions, but that would be your assignment. Okay, so I'll post that. It's already posted, but I've got to make sure that that typo I had in there gets fixed. So I'll fix that typo. You'll be able to go up in here. Also, I will post the recording and the link to the recording so that you guys can watch this all again. And if I have time, I might even add a little bit more going through some of these examples I didn't have time for and put that on there. I might do that because I just hate to not have had enough time for this. Okay, well, I'll let you guys go. Please let me know if you have any questions, and I'll talk to you guys on Monday. I will make that assignment. I'll even assign this week's later, because I think even some people still don't maybe have their Zybooks yet. So I'm still going to be a little lenient for this assignment. But anyway, I'll talk to you guys on next Monday. Okay, bye guys. Have a good weekend, or a good week and weekend.
Thanks, you too.
Okay.
Thank you.
Bye-bye.